We're going to be covering integration by parts today, and this is a special integration technique. It undoes the product rule, but it's for special products only. It doesn't work for every product. Okay, so let's just refresh on what product rule says. Product rule says that the derivative of a product of two functions, f of x times g of x, is the first times the derivative of the second, plus the second times the derivative of the first. So I have f of x times g prime plus g times f prime. Okay, so that's first derivative second plus second derivative first. Now, if that's what product rule says, and my integration by parts is going to undo product rule, I'm going to write this backwards. And I'll have that the integral of fg prime plus gf prime, which is my product rule, my first derivative second plus second derivative first, is equal to f times g plus c. Of course, I need a constant of integration. Okay, so all I did was I took this stuff and I put it inside an integral, and I got back this stuff plus a constant of integration. Okay? Now, that integral looks awful, okay? We're never going to see an integral that's that complicated. It's too many terms, too much stuff going on. We're never going to see that, so we're going to break it up. Okay, so I split the integral into two pieces. So instead of having the integral of fg prime plus gf prime dx, I have the integral of fg prime dx plus the integral of gf prime dx is equal to f of x times g of x plus c. Okay, I left the right side the same. Okay, and now again, we're never going to see an integral we're never going to have a problem that's two integrals. Okay, I have two separate integrals here. So I'm going to solve for this first integral. Okay, and I'm going to solve for that first integral by just subtracting this part from both sides. Okay, so I'm just going to do a little algebra to subtract this integral to bring it over to the side, and this is what that will look like. Okay, so I subtracted this integral, and I brought it to the other side, and so I have f times g minus the integral of g times f prime, so minus that integral, plus my constant of integration, of course. Okay, and that is my integration by parts rule. Okay, this loveliness down here. The reality is that that looks like a big hot mess, and we're never going to remember that the integral of fg prime is equal to fg minus the integral of g f prime. So we have a method to remember this, okay, and that method is by doing, or just renaming our pieces, okay. So we're going to let u equal f of x and v equal g of x, okay? And we're not doing a substitution. We're just renaming pieces so that we can have a little bit of an ease for using them, okay? So I'm going to let u equal f of x, okay? And v is g of x. So I have u as my f of x. Okay, my f of x shows up twice here. My v is my g of x. My g of x shows up twice here. Okay, the problem is that I also have these other pieces that I haven't taken care of yet. Okay, I have my g prime of x, and I have my f prime of x. And I have these dx's floating around, so I'm going to need to also find those pieces. Okay, so we also need to figure out what my f prime of x is and what my g prime of x is. So in order to do that, I'm going to need to take some derivatives. So find me what du is and what dv is in terms of f of x and g of x. Pause and come back. So you should have come up with the fact that if u is f of x, then its derivative du would be f prime of x dx. And if v is g of x, then its derivative dv would be g prime of x dx. Okay, now we're going to make a full substitution, and we're going to put in, every place we see an f of x, we're going to put in a u, and every place we see a g of x, we're going to put in a v, and every time we see a f prime of x dx, we can put in du, and every time we see g prime of x dx, we can put in a dv. I started it for you, okay, so for you, get it? No, okay, so u is f of x, I have the integral of f of x, so I have the integral of u, all right, and then my g prime of x dx, that's my dv, so I have the integral of u dv. So go ahead and finish that up. Every time you see an f of x, put in a u, g of x v, f prime of x dx du, g prime of x dx dv. So go ahead and finish that substitution. And you should have come up with this, that the integral of u dv is equal to uv minus the integral of v du. Now, I don't know whose big idea it was to have u's and v's floating around the same problem. We have a bunch of situations in math where we're like, what are they thinking? But that is our big finish, okay? And that's what we're going to be working with. Okay, and for some reason, this is going to stick in your head. The integral of u dv is equal to uv minus the integral of v du. It just sticks. Let's talk about the pieces. Okay, let's let's think about what those pieces represent and how it's going to impact how we do our problem. Okay, if this is what I'm starting with, okay, then that's what I need to think about. Okay, so I have a u and a dv, so I'm going to start by, my first step is going to be to pick u and to pick dv. Okay, but just like we saw with that other stuff, I don't not only have a u and a dv, but I also have a v and a du. So our second step is going to find v and to find du. Okay, so we're going to start by picking u and dv. Our second step is going to be to find v and to find du. There's some strategy that goes into this. Okay, so our biggest strategy is to realize that to get from dv to v, we're going to need to integrate, right? To get from a dv to a v, you need an antiderivative, okay? So when we're integrating, our functions usually become more complicated. Like if I integrate x squared, then I end up with an x cubed over 3. Going from an x squared to an x cubed, that's a bigger function. It's a more complicated function. So generally when we're picking our dv, we want to pick it so that when we integrate it, it will become no more complicated. And then in the same vein, we're going from a u to a du. We're going to be taking a derivative to get from u to du. So we generally want to pick a function that's going to get simpler when we take its derivative. But the more crucial thing is that when I'm integrating, I can't have a function get more complicated because it will turn around to bite me in the butt. And then just as a general reminder that if you have a definite integral in your problem, just hold your bounds to the very end. Otherwise, it just gets a little too complicated. Okay, let's do some examples. Let's start with the integral of x times cosine x dx. Okay, if you try, again, this is a product. If you try a normal u substitution on this, you're going to get nowhere with it. U equals x is never going to get anywhere with you. If you let u equal cosine, your du is going to have a sign in it, and that's not going to get anywhere. So a normal u sub is not going to work on this. All right, but this is going to be an integration by parts problem. Okay, so we're going to start by picking u and dv. Okay, and after we pick our u and our dv, we're going to go back and we're going to find du and v. Okay, so some strategy. We want to pick, our main concern is on that dv side. Okay, I want to integrate it and have my function get no worse. Okay, so my choices for my u and for my dv are going to include either the x or the cosine x, and the dx would go on the dv side. Okay, so what can I integrate that's not going to get any more complicated? If I integrate x, I'm going to end up with an x squared over 2. That is getting more complicated, versus if I integrate cosine x, I'm going to have a sine x, and that's not getting any more complicated. It's just staying a trig function. So let's pick our dv to be cosine x. Okay, and what I was saying with this not getting any more complicated, or I'm sorry, what I was saying with the dx is if I'm going to integrate this, I'm going to need a differential at the end so that I can integrate it. Okay, and that's going to leave on my other side, my u is going to be my x. Okay, so all of our pieces are accounted for. So this is my dv, my x is my u, and again, we're not doing a substitution, we're just rearranging our terms, and our goal is to get a simpler integral. Okay, so you'll see how that's going to play out here. So now that we have u and dv, I want you to go ahead, pause the video, and find me du and find me v. We're going to find du by taking a derivative and v by taking an antiderivative. Pause and come back to me. Okay, so the derivative of u, du, the derivative of x is 1 dx. Okay, and on this side I'm going to be integrating. All right, and the integral of dv is v, and the integral cosine x dx is going to be sine x. We don't worry about a constant of integration until the end. We're going to have a bunch of constants of integration floating around if we worry about it too soon, so we just save it for the end. Okay, and now I'm going to rewrite and do uv minus the integral of v du. Okay, so uv minus the integral of v du would look like uv, x times sine x, minus the integral of v du, minus the integral of sine x dx. Okay, so really what you need to understand about integration by parts is that it's a trick to go from an awful integral to a cute, sweet little integral. Okay, you might not get there immediately when you do integration by parts, but you should get there eventually. And now we can integrate this new integral much more easily than this original integral. So I'm going to hold that x sine x, and minus the integral of sine x would be negative cosine x. So plus cosine x plus c, and that's my answer. Okay, and the nice thing about a problem like this is you could actually go ahead and take the derivative of this and get back to what you started with, and you'll see how it all pans out. Okay, so, and again, if you had picked the wrong, if you had swapped u and dv, you would see that your new integral was awful instead of better, and when your new integral is worse, that is a good indication that you picked the wrong u and dv and that you should start again. Let's do another. Okay, so here's a definite integral problem, and like I said, we're just going to kind of ignore those bounds until we get to the end. All right, so let's talk about what our u and our dv should be. Again, I've got my t and I've got my e to the 2t going. Which of these can I integrate without my function getting any worse? So think about that. Pause if you need to. But my exponential function I can integrate without getting any worse, so I'm going to put my e to the 2t dt over here. Okay, and then that would leave my u be just my t. Okay, go ahead and pause and find du and find v and come back to me. Okay, so du would just be, the derivative of t is 1 dt. Okay, when I go to take the integral on this side to get to v, that is a composite function, so you will need a u sub. Okay, if you need to do the full u sub out, go ahead, your u would be the exponent, u would be 2t. Okay, and your du would have a 2 dt in it, so you'd need a 1/2 coefficient, so I'd have 1/2 e to the 2t. Okay, I don't need to see your u substitutions at this stage. You guys are doing pretty good with them, but if you need to do them, then you do them, and you make sure you get the problem right. Okay, but again, you can also take the derivative of this to double check. So the e to the 2t would be what you see is what you get, e to the 2t times the derivative of the exponent, so times 2, which would take care of that 1/2 coefficient, and I would get back to what I started with. All right, so I'm going to go ahead and do my uv minus the integral of v du, pause, and come back. I would have uv, so t times 1/2 e to the 2t, or 1/2 t e to the 2t, okay, minus the integral of v du, so minus 1/2 e to the 2t dt. I don't think I actually said my integral there. What I'm going to do so that I don't forget that I had bounds is I'm going to throw them on right here, so from 0 to 1, and I'm going to throw them on here. Okay, but I'm not going to actually do anything until I'm done integrating. So for this first piece, I have a 1/2 t e to the 2t. Okay, the good thing about this is that it's always going to be a repeat integral when there is a u substitution involved. So I just integrated e to the 2t and got 1/2 e to the 2t. So when I integrate my e to the 2t, I'm going to have a 1/2 e to the 2t times 1/2. So I will have minus 1/4 e to the 2t. Okay, and I'm going from 0 to 1. Okay, so I'm going to do upper bound minus lower bound on this. So go ahead, pause, and come back to me. Plugging in upper minus plugging in lower, I will have 1/2 times 1 times e to the second minus 1/4 e to the second. And then plug in 0, I'll have minus 1/2 times 0, which will give me a 0, minus a negative, so plus 1/4 e to the 0. Okay, and that'll give me my a 1 at the end. So if I simplify this, I have a 1/2 e squared minus 1/4 e squared. That's going to be a 1/4 e squared plus 1/4 e to the first, I'm sorry, e to the 0, which is 1, and 1, so I'll have plus 1/4. And that's my answer. Okay, I'm going to be out of time. I'm going to do another video. I'm going to show you guys the tabular shortcut method and some more examples. Okay, so see the next video for more information.